just gonna stand there. Welcome back to physics, and today we are going to start talking about forces at angles.
So in one of our previous videos, I guess I must have fallen off a cliff and died. So in this video, Miss Becker is going to bury my dead body by dragging me across the ground to the spot where she's going to bury me. I think that's what we're going to do. So today we're going to talk about forces at angles, and this makes a lot of sense because when we do problems in physics, we usually say that we're pulling something horizontally. So we attach a rope to an object and we pull it horizontally. But how often does that actually happen in real life? Most of the times, you're pulling something across the ground that's low to the ground. Like, let's say Christmas is coming up and Christmas vacation is coming up, and you're going to be pulling a sled behind you. You don't get down and pull the sled horizontally like this. It doesn't work. You pull with the rope at an angle. So in real life, we usually apply forces at angles. There's a problem with that. So when you pull a dead body at an angle, you're pulling in two different directions at the same time. So let's say, well, let's give myself a mass. Let's say I'm 100 kilograms. Just a nice round number that we pulled out of my head there. 100 kilograms. And you pull with, I don't know, make up a force. It's got to be a big force.
300 newtons.
Pull with 300 newtons. Now the first question is, well, that's 300 newtons, just like our projectile motion rocket problem. That's 300 newtons at some angle. So let's say we're pulling at an angle of...
Let's do 37 degrees.
That's a weird number, but
I
37
know.
degrees. Now, that means you're pulling horizontally with some amount of force and vertically with some amount of force. So the first question is going to be, well, what's the x component of that force, and what's the y component of that force?
Now, luckily, we've already kind of talked about that stuff. We've talked about finding our x component of something and our y component of something, and we have those equations on the back of our reference table. So remember, we have ax equals a cos theta, and we have ay equals a sine theta. Now, a stands for any vector. So when we talked about this previously, and we were talking about projectiles fired at an angle, we were talking about the velocity they were fired with. So we changed those to be Vx equals V cos theta and Vy equals V sine theta. Well, now we're talking about a force.
Hold on, before we move on any further, make sure you understand what you put into this equation and what you get out of the equation. If you put force as a vector and that force times cosine the angle, you will get a force as an answer. If you put a velocity and multiply by the cosine angle, you get a velocity as an answer. Can you do this with distance? And the answer is no. You cannot put a distance in here, multiply it by the cosine of the angle, and get a distance for an answer. The reason is because this stands for any vector, and distances are not vectors.
Okay, so if we plug in, we're plugging in our force, so our overall force is 300 newtons times the cosine of 37 degrees. And for this one, we're doing 300 newtons times the sine of 37 degrees. So we get an x component, which I'm going to label on my diagram, of, we'll round it to 240 newtons for an x component and 181 newtons for a y component.
Okay, so now we know what we're pulling up with 181 newtons, and we're also pulling that way to the right, yes, to the right of 240 newtons. Now, the next question is going to be, what is Fn on the dead body? Now, Fn, normal force, is normally equal to Fg. But is that true in this case? We'll stop, let you think about it. Okay, ready? Is Fn equal to Fg in this case? And the answer is no. Why? Because you're pulling up with 181 newtons of force. So then the question is, how much force does the ground actually feel? So let's calculate our Fn.
Before we do that, let's just finish drawing out our free body diagram. So we have this applied force here that I'm pulling with. What other forces should we be adding to our free body diagram? Well, you should know that we always add in our weight, or our force due to gravity, and we're going to add in our normal force, because his body is on a surface. So the surface has to be pushing up on him with some sort of force. Like we said, we're not positive what it is yet, but there has to be some sort of force he's pushing up with. The other thing is, his body's sliding along the floor. If we're sliding, you should remember we have to have some sort of a friction. If he's sliding on dirt, it's not frictionless. So we have some sort of friction, which we can talk about as well. So now let's calculate that Fn. Now, in order to do that, we have to think, is his body accelerating up or down? The answer is no. So what that tells us is that our F net in the y direction has to equal 0.
And notice what she did here. Before, we were just talking about F net, and we just said F net is 0. But now she split it up into F net y, and she'll eventually also do an F net x. Why? Because we want the net force in the y direction, and we want the net force in the x direction. Normally, when we have done this before, we have just said that Fn and Fg are equal, therefore F net in the y is 0. But that's not true in this case, because you're lifting, or she's lifting a little bit up, straight up. So, how much force does the ground actually feel? So, if we added Fn and her y force, what would it have to be equal to?
So when we're figuring out our net force, we add up all of our forces in that direction. Net just means sum of the forces. So we have Fn going up, we have our Fa in the y direction going up, and we have our force due to gravity going down. So that force due to gravity is in the opposite direction, so I have to put a negative on it when I set it equal to 0. I can then move that Fg over to get where he was going.
This just means net. Net means the sum of all the forces. So the question could be, well, why is Fg negative? And like she said, it's because it's in the opposite direction. You would add up all those forces, but you need to subtract Fg because it's down where the other ones are up.
So that means instead of our normal force just equaling our force due to gravity, our normal force plus our applied force in that y direction equals our force due to gravity. Now in the past, that has just been 0. So this has always been true, we just haven't had any applied force in the y direction. Now we have one. So we have to add that piece in there. So if we want to go ahead and solve that and try and figure out what our Fn is, when I go to plug that in, so I have Fn, our normal force, plus our 181 newtons in the y direction, and that's going to equal his weight. Now, is this 100 kilograms his weight?
Common mistake for a lot of people. 100 kilograms is not weight, it's mass. So how do you find weight if you're given mass? Take your mass, multiply it by 9.81. So,
we picked a nice easy number, 981 newtons.
So now you can find Fn by just subtracting out the amount of force that she pulled up.
See, you thought my angle was weird and it made our lives nice and easy.
Yep.
So we get a normal force of 800 newtons.
Now, what that means is, because she pulled up with a little bit of force, the floor or the ground or whatever I'm dead laying on top of felt less of my weight. How much less? 181 newtons less, because that's what she pulled up with. Next question could be, well, what's my acceleration as a dead body as she's dragging me across the floor? Well, my acceleration would then be in the x direction. So now we have to find F net x. For this one, to shorten this up a little bit, let's say it's a frictionless surface. That way we don't have to worry about what the net force is going to be, because if it's frictionless, there is no friction, which means our net force in the x direction is just going to be a sub x. So she'll erase that and she'll write F net x is equal to Fax.
Now, if there was friction, what was that, 800?
Yeah, just leaving that right there.
If there was friction, the only thing we would have to do different is we would have to add minus FF. the FF is working in the opposite direction. But since that's 0, it goes away.
We will do problems like that. We're just avoiding it right now just to save time in the video.
But keep that in mind, you would just have to subtract it out, but FAX minus 0 is just FAX. So, my net force, we also know that our net force always equals mass times acceleration in that same direction.
Always.
And that's going to equal my FAX. So when I go to plug in, we have our mass of 100 kilograms. I'm trying to solve for my acceleration, and we found before that our force in the x direction applied was 240 newtons. Again, nice some simple math here. We don't have to even grab a calculator. 2.4 meters per second squared.
So my dead body would be accelerating across the floor at a rate of 2.4 meters per second squared. Now, that's a constant acceleration. As long as she kept pulling with the same amount of force, I would constantly accelerate at 2.4 meters per second squared. After the first full second of her pulling me, I'm doing 2.4 meters per second. After 2 seconds, I'm doing 4.8 meters per second. Which means at some point, she's going to have to be running with my dead body. Good luck with that.
Hopefully there's some rocks. So, as you can see, there's a lot more places we can go with this. This is only the beginning with our forces at an angle. But all we're doing is combining some of the other things that we've talked about. We've seen finding our components in projectile motion. We talked about net force before. We talked about our accelerations. We're just adding another little layer of complexity. So if any of this old stuff is still giving you issues, please come to extra help because it's just going to get worse.
I feel like we keep saying that over and over again, but it's so totally true.
So any questions that you have, please ask. We're going to keep doing a ton more practice on this, and your upcoming test is next Friday, December 15th. So just keep that in the back of your heads.
See you at Extra Help, and have a good night.